Okay, let's get started. So today we're going to be going through the idea of a series. Okay, so given a sequence AN, so we know what a sequence is from last time. Okay, so it's some infinite number of terms indexed by this n. So for example, we can have AN equals 2 over 1 plus n, for example. We can substitute different natural numbers n and we get different elements in the sequence. Okay, so what we want to do now is take the sequence and sum up all those infinite terms. So we want the sum from n equals 1 to infinity of an. So we'll see there's a few examples where we can calculate this value exactly to see what the sum is. Other times we can't do that. And in those cases, we just want to see, is the sum finite or not? Okay, does the sum go to infinity or does it go to some finite value? Okay, in other words, we want to check, does the series converge? Okay, so we would like to check if the series or infinite sum converges. Okay, if it doesn't converge to a finite value, then we say that it diverges, so it goes off to infinity. Okay, so we'll start off with a few examples just to show how this can be tricky, and then we'll look at the tests for convergence. So it's techniques and tricks that we can use to make finding if this converges or not a bit easier. Okay, so we'll start off with a very simple example. So let's say the sequence was just n. So the sequence goes 1, 2, 3, 4, and so on. So now if we want to find the sum of all these terms, we have the sum from 1 to infinity of n. So this is going to be 1 plus 2 plus 3 plus 4, dot, dot, dot. This is clearly going to be infinity, right? So each term, next term is bigger than the previous one. So if we have 1 plus 2, that will be 3. If we add 3, it will get bigger and bigger and bigger. And then if we add more and more terms, the sum just goes off to infinity. So this series diverges. Okay, so that's very clear to see that this one diverges. For this next example, you may think it converges, but it's a bit tricky. So let's say an equals 1 over n. Okay, so now with this one, we want to find the sum as n goes from 1 to infinity, 1 over n. So here we have 1 plus a half, plus a third, plus a quarter, and so on all the way to infinity. Now with this one, it's not so obvious. We see that each next term is smaller than the previous one. So we start off with 1, and then we add something smaller than 1. Then we're adding something that's smaller, again, a third, and then a quarter is smaller, and then a fifth is smaller. So as we go on, we're adding smaller and smaller terms each time, but in fact, this also diverges. So this series also diverges. Okay, so that's a bit surprising. So even though we're adding smaller and smaller terms, and in the limit we're essentially adding 0 because 1 over n goes to 0, but this does diverge. Okay, and we'll see a quick little proof of that. Okay, so let's say we've got our series here. 1 plus a half plus a third plus a quarter. We'll just put a few down just to show. Okay, plus 1 over 6, plus 1 over 7, plus 1 over 8, plus 1 over 9, plus dot, dot, dot. And then that goes all the way to infinity. What we want to show is that even though the terms are getting smaller and smaller, the total sum is still infinite. Okay, so how do we do that? So what we want to do is replace each term with something that is smaller than or equal to. Okay, So this is going to be bigger than or equal to this new series, but each term I'm going to replace with something that has the same value or smaller. Okay, which means the series on the right, or in this next line, will be smaller. We'll show that that one is infinity, which means the first one is infinity. Okay, so let's see what I mean. So 1 we'll leave alone, a half we'll leave alone, and then a third and a quarter, we'll group that together. We're going to replace 1/3 with 1/4, so it's getting smaller. So we're going to have plus 1/4 plus 1/4, we'll leave that one alone. Then for these next few, so 1/5 to 1/8, we're going to replace with something smaller. So 1/5 we're going to replace with 1/8, that's smaller. 1/6, that's bigger than 1/8, so that's 1/8 will be smaller, that will be smaller, and that will be the same. Okay, so each term I'm replacing with something smaller than or equal to. Then for the next lot, I'm going to replace with 1/16 all the way down, and then it goes on like that with these powers of 2. Okay, so now we've got a new series which is smaller than the original. So each term here, this one is smaller, the 1/8 is smaller than a fifth, 1/8 is smaller than a sixth, 1/8 is smaller than a seventh. So each of them are, in fact, smaller. But now let's try sum them up, and we'll see something. So the 1 stays, then we have a half. A quarter plus a quarter, that's a half. 1/8 plus 1/8 plus 1/8 plus 1/8, that's 4/8, which is 1/2. For the next grouping, we're going to have 1/16 plus and so on. We're going to have 8 of those. So 8/16, that will be a half. And the same thing applies to all those groups that I made. So now we have 1 plus a half plus a half plus a half plus a half and so on. We can simplify this even further. The half plus a half, that's a 1. The next half plus a half, that's another 1. Plus 1 plus 1 all the way. And that's infinity. So what we showed here is that our original series is bigger than infinity. But the only way for it to be bigger than infinity is if it diverged itself. So therefore, 1 plus a half plus a third plus a fourth plus dot dot dot, this is actually infinity. So just because the terms are getting smaller and smaller doesn't mean it converges. So there's actually more that we need to show. So it's true that they do need to get smaller and smaller, but there's more. Okay, so you can't just assume that because the terms are getting smaller and smaller, that it will converge. Okay, so this is a counter example to that. Okay, and then the final example, so number 3, okay, just to illustrate this idea, is if we have the sum from n equals 1 to infinity of 1 over n squared. So for this previous one, we had 1 over n. So 1 plus a half plus a third and so on. Here will be 1 over n squared. Okay, now we won't go through the proof. That's a bit too much. But in fact, this does converge, and it converges to pi squared over 6. Okay, so weird number. We're not going to go into the proof for that. But all we need to know is that this number is less than infinity. So it converges. Okay. So for most of these series, we're not interested in the exact value. Okay. All we're interested in, does it diverge to infinity or does it converge to something finite? Okay. So most of the time, we're not going to find what that value is, but we will show if it is finite or not. Okay, so you see there's a little difference. So 1 over n, that diverges, but 1 over n squared, that converges. So even though these series look very similar, they have different behaviors. Okay, so it's very easy to get tricked by some of these. Okay, it may look like it converges from what you've seen before, but it might in fact diverge. Okay, so it's very important that you go through these tests. Yeah, question? There's a proof for that, but you don't need to know that. This is just an example to show that it converges. Okay. I'll show you now later on when we look at the P-series test. If this exponent here is bigger than 1, it converges. So you don't need to know the exact value. This is just to show you what it actually is. Okay. But some of them we can find the value. Like if we have a geometric series, we can sum up a geometric series and that will have a nice value. But for some of them, we won't be interested in that. Okay, so instead of trying to find what this value actually is, we're going to use the convergence tests. Okay, so there's a few tests that we use to check if it converges or diverges. Okay, so it's a nice list of them. We'll see with plenty of examples where to use them, but for the tests and assessments, I won't say which test to use. Okay, so you will need to know which test to use for which series. Okay, but you'll see for most of them, it's quite obvious which one to use. For some of them, you can use different ones. So you might use test number 1 or test number 2. You'll get the same answer. So that will be up to you to decide. Okay, so let's have a look at them. Series convergence tests. Okay, so there's quite a few of them, and it just tells us if it converges or diverges. So the first one is called the test for divergence. Okay, so that's the name. Please, when you are doing your assessments, please put the name of the test that you're using so I can see what you're doing. So some of them, the working is quite similar, so I do need to know which method you're using. So just put the name down and then you can put your working and I can see what you're trying to do. Okay, so for the test for divergence, what we want is to calculate the limit as n goes to infinity of the sequence. Okay, so remember for a series, we're summing up a sequence. We look at these sequence values here, an, we take the limit. If the limit does not exist, or the limit is non-zero, then it diverges. N equals 1 to infinity, an diverges. Okay, so this is what I was saying at the beginning about adding smaller and smaller terms each time. So here, if we take the limit as n goes to infinity of our sequence, if the limit is not 0, then it means we're adding bigger and bigger terms each time, and so it goes to infinity. Okay, so if the limit is 0, it doesn't mean it converges, so it doesn't go both ways. If the limit is non-zero, we know it diverges. If the limit is 0, we can't say what happens. Okay, so here again, limit non-zero diverges. Okay, so that's the first test that we can use. Number 2 is the integral test. Okay, so here we define a function f. Okay, so f such that f of n is equal to an. Okay, so whatever our sequence was, we use that to define a function. For example, if an was 2n over 1 plus n squared, then f of n would be 2n over 1 plus n squared. Okay, so we just define this function f. Now, there's a few conditions that we need to look at before we do the calculation. So f needs to be continuous. It needs to be positive. It needs to be decreasing, okay, on the interval 1 to infinity. Okay, so our natural numbers start from 1 and then they go to infinity. Then our series, sum from n equals 1 to infinity an, converges if and only if the integral from 1 to infinity f of n, f of x dx converges. Okay, so what this means is we can look at the sequence as a function. We replace n with x, so instead of a natural number, we put a continuous variable x. We calculate this integral. If the integral converges, then our series also converges. If the integral diverges, then our series also diverges. Okay, but remember f needs to satisfy these conditions first. Okay, if f does not satisfy these conditions, then we can't use this test. Okay, so let's put the other one down. So n equals 1 to infinity, an diverges if and only if the integral from 1 to infinity f of x dx diverges. So they both converge or they both diverge. Okay, so that is the integral test. Okay, number 3, the comparison test. Okay, so this is where we compare our series to one that we know either converges or diverges. Okay, so as we go through these examples, you build up a collection of series that you know will diverge or you know will converge, and then you can use those to test other series. So one of them that we know now, the sum from n equals 1 to infinity of 1 over n, we know that diverges. So we can use that later on. We also know that the sum from 1 to infinity of 1 over n squared converges. We had that earlier, so we can use that to test other series. Okay, so how do we do that? So if we have a series here, n equals 1 to infinity, bn converges, so we know this is true, okay? Either from homework or from the lectures, we know this is true. And an is less than or equal to bn. Okay, so this is how we do our comparison. So an, that's the one we're testing. Bn, that's the one that we know. Then we know that the sum from n equals 1 to infinity, an, also converges. Okay, so if the series that we're testing is smaller than the one that we know, and the one that we know converges, then the one that we don't know will also converge. Yeah. So the one that we don't know, an, so put a little question mark there. If the one that we don't know is smaller than something that converges, then it automatically converges as well. On the other hand, if we have the sum from n equals 1 to infinity, bn diverges, and an is bigger, again, an, that's the one that we don't know. If that's bigger, then it also diverges. Okay, so to summarize, if the unknown one is smaller than a convergent series, it converges. If the unknown series is bigger than a divergent series, then it diverges. Okay, so that's just a summary of what these two mean. Okay, so that is the comparison test. Yes? Yep. If it's equal to, then we know already if it diverges. On the first one? No, it stays like that. So you can remove it if you want, but having it like that is fine. Yeah. Yeah, if it's equal, then it means it's the same series, so you don't need to worry. So you can remove it. Let's write here. Okay, so you can put it like that. If you put an equal to sign, it doesn't change anything. It stays the same. Okay, but yeah, if you want to remove it, that's fine as well. Sorry? Yeah, so which So you want it less than?
No, if it's less or equal.
Yeah, so if this bigger one converges, so this is the one that we know, the smaller one is the one that we don't know. If it's smaller than, then it converges as well. Yes?
This question is if they're both equal, then does it converge?
Converge. Yeah, because if they're equal, then it's the same. So if AN equals BN, then if the one converges, the other one also converges because they're the same. Okay. Yeah, so it doesn't matter. You can keep it like that. It's the same. Okay, so that's the comparison test. Number 4 is the limit comparison test. Okay, so we've got the comparison test, and then we've got the limit comparison test. Okay, so they're two different things. So for the limit comparison test, what we want to do is calculate the limit as n goes to infinity of an over bn. Okay, so those are two different series. So an is the one that's given to you, bn, that's the one that you know. If this is greater than 0, then both converge. Or both diverge. Okay, so again, Bn, that is one that you would know. Okay, so like 1 over n squared, something like that. You would know what this one is. An, that's the one that's given to you. And you use this Bn as a test. So you calculate this limit. If it's bigger than 0, then both of them will converge, or both of them will diverge. Okay, so that depends on this Bn. So you choose that one. So you either choose something that converges and test it, or you choose something that converges and then you test it. Okay, so that is greater than 0. Then we have the limit as n goes to infinity, an over bn. If it is equal to 0, and, so you need to check both of these conditions, and the sum n equals 1 to infinity, bn converges. Okay, so you have the limit going to 0, and the bottom one converges, then the top one also converges. Okay, so that is when that bottom one converges. So we know if the bottom one there converges, then the top one also converges if the limit is 0. Okay, and then the last one with this, limit n goes to infinity, an over bn. If this is infinite, and the bottom one diverges, okay, so the bottom one, if the limit's infinity and the bottom one diverges, then that means the top one diverges. Okay, so that's the limit comparison test. Then, number 5, we have the alternating series test. Okay, so here if we have an alternating series, so this means it goes positive, negative, as we go down the line. So we can write it as minus 1 to the n plus 1 times bn. So we see here if n is 1, then it's minus 1 squared, so it's positive. If n is 2, then it's minus 1 cubed, which is a minus, so we get a minus bn, and then it alternates between positive and negative. Okay, a few conditions. Bn must be positive and decreasing. Okay, so what we have is an alternating sequence. It goes positive, negative, like that, but it's decreasing. So a little picture of what's going on, we have something like this. Okay, so each of these terms, the minus 1 to the n plus 1 bn, so this part over here, it will be positive, negative, but since bn is decreasing, we see that they converge to some point. Okay, so if that is true, then we calculate the limit as n goes to infinity of bn. If this is 0, so the terms get smaller and smaller as we go, then that means it converges. Okay, so even though they're alternating, they're still getting smaller and smaller. So since the terms are getting smaller and smaller as we go along, the series converges. Okay, so that's the alternating series test. Number 6 is the absolute convergence test. Okay, so this one's quite simple to state. If we have the sum as n goes from 1 to infinity of the absolute value of an, if this converges, so given some an, if we can take the absolute value and it converges, then the original one also converges. Okay, so we call that absolute convergence. Okay, because if we take the absolute value, it converges. Okay, a few more to go through. So number 7 is the ratio test. Okay, so here we take the ratio of consecutive terms, so an and an plus 1, and we check if they're getting smaller or not. So very similar to what we did with sequences to see if it was increasing or decreasing. So here we take the limits as n goes to infinity of an plus 1 over an. So the next one divided by the current one. If this is less than 1, okay, so if it's less than 1, it means an is bigger than an plus 1, then it converges. Okay, and then if it's the other way around, then we know that it diverges. So we have the limits as n goes to infinity, an plus 1 over an. If it is greater than 1, then it diverges. Okay, so now this is greater than 1 or less than 1. If it is equal to 1, then we can't say anything. We need to do another test. Okay, so if the limit is equal to 1, then it is inconclusive. Okay, which means try something else. Okay, so it must be either less than 1 or greater than 1. It can't be equal to 1. If it is equal to 1, you need to try another test. Okay, so that is the ratio test. Next one, okay, is the root test. Okay, so here we take the limits as n goes to infinity, an to the 1 over n. So we take the nth root of the nth term, so 1 over n is the nth root. If this is less than 1, then it converges. Okay, if it is greater than 1, it diverges. Okay, greater than 1 diverges. You don't need to take photos of anything. The notes are always available online. Okay, so it diverges, and again, similar to the previous one, if it is equal to 1, it's inconclusive, we need to try something else. Okay, so we try something else. If the limit is equal to 1. Okay, so same like the previous one. If you end up with a limit value of 1, then you need to try another test. Okay, 2 more. Number 9, the P-series test. Okay, so for this one, we are interested in series of the following form. So we have the sum from n equals 1 to infinity, 1 over n to the p, so that's the power, p for power. Okay, so if we have any series like this, we can immediately test for convergence based on the value of p. So if p, or the power, is greater than 1, then it converges. Okay, so that's the simplest one. So if we have 1 over n, we know that the power is 1. Okay, 1 is not greater than 1, so we know it diverges. If we have 1 over n squared, 2 is greater than 1, so that means it converges. So if you're using this P-series test, you need to tell me what the value of P is. You need to show that it's greater than 1, and then that means it converges. Okay, and this works for integers and fractions and so on. So if P is 3 over 2, okay, if that's greater than 1, so we know it converges. So it doesn't have to be like squared or cubed or anything like that. You can have 5 over 4, for example. That would be greater than 1, so it converges. Okay, but if it's 4 over 5, that's less than 1, so we know it diverges. Okay, and then the last one, number 10, is the geometric series test. The geometric series test. Okay, so for this one, we're interested in those geometric series, like from high school. So we have the sum from n equals 1 to infinity, ar to the n, like that. Okay, so we've got some a value, and r, we know that's the ratio between the terms. It can be either positive or negative, this ratio r, so it could be alternating. But if the absolute value of r is less than 1, okay, so it must be less than 1, it can't be equal to 1, then it automatically converges. Okay, so that ratio between the terms, if it is less than 1, it means the terms are getting smaller and smaller, and they're getting small enough such that it converges. Okay, if it is equal to 1 or bigger, then we know that it automatically diverges. Okay, so those are the 10 series tests. Okay, so some of them will be very obvious to use. For example, the geometric series, you can see what that will be. For the P-series, you can see when to use that. For the other ones, you just need to go through the examples. Okay, so I will upload a follow-up video going through the examples, and that will show you when to use the different tests. Okay, so in the examples, you'll see things like the sum from n equals 1 to infinity, n over 1 plus n squared, for example. So if you see something like this from the examples, then in the test, if you see something like this, you know which test to use. Okay. And there are, I think, around 20 examples that I'll cover later on, so you can see from those, and then the tutorials as well. There'll be more examples. Okay, so there's no set rules on what to use for what, it's just practice. Okay, so you'll have to look at the examples from the lectures, the examples from the tutorials, and any additional examples that you can find, and that will tell you when to use the different tests. Okay, so again, in the assessments, I won't tell you which test to use, you need to know which one. Okay, that will count towards the marks. So knowing which test to use, that will count for some marks. Doing the calculations, like finding the limits and so on, that will count. And then finally, your conclusion. So does it converge or does it diverge? That will also count for marks. Okay, so it can be like around 5 marks. Okay, so that's going to be it for today. I will upload that video later. I'll let you know when it's available. For Thursday, before we start the tutorial, we'll have a quiz on sequences. So bounded sequences, convergent sequences, something like that. It will only be 10 minutes, so it won't be too long. Then you'll have the tutorial. You can work in groups and so on. And then at the end of the tutorial, the tutors will be collecting your work. Okay, so please make sure that you have your pages available for the tutors to collect. Okay, please make sure your names and your student numbers are on all the pages as well. Okay, just so things don't go missing. Okay, so I'll send you an email when that other video is available, and then you can go through it. Okay, if you have any questions about the tutorial while you're going through it, please just come to my office. I can help you out, or you can email me. Okay, so I'll see you in the tutorial.